Okay, so the following proof is important because what it's going to show is that every rational number that we can write in our modern notation in modern mathematics, every rational number that we can write between 0 and 1 can be written as an Egyptian expression, and an Egyptian expression is just a sum of unit fractions, because the ancient Egyptians would write all of their fractions as just sums of unit fractions. So we want to see if we can actually write all of our numbers in Egyptian number, all of our fractions in Egyptian fractions on this interval. So let's start with a proof. So we're going to start with some definitions. Rho, we're going to say rho is equal to P over Q, with P over Q being in between 0 and 1. And we're going to let S be the set of rational numbers rho. Then every rho in S can be expressed as a proper reduced fraction. Rho is equal to P over Q. So I just repeated myself here. Now we can write Q is equal to 2 to the n times Q naught. So we're just defining Q like that. And remember that Q is in the denominator. So we just have Q equal 2 to the n times Q naught. Times Q prime, where n is some integer greater than or equal to 0, and Q prime is odd. So it's an odd integer. So what we're going to do next is we're going to partition the set S into two disjoint subsets. So let's see what's going on here. So we can separate the set S and partition it into these two classes A and B, so that rho is in A if P is less than 2 to the n plus 1. So that's how we're defining rho being in A. So if P, the numerator, is less than 2 to the n plus 1, then rho is in A. And we're going to define rho being in P if P is greater than or equal to 2 to the n plus 1. So it's obvious from here that the two sets are mutually exclusive. Okay, so side note, if Q prime is equal to 1, then P is less than 2 to the n. So P is an element of, so rho is an element of A. Okay, so that's just a side note. Let's get to defining what happens if rho is in A. So if rho is in A, then P is less than 2 to the n if Q prime is equal to 1, which we already talked about over here. And for P less than 2 to the n plus 1, we can write the following equation. P is equal to the sum of J in capital J of 2 to the J, where capital J is a subset of the set 0, 1, 2, n. And we obtain the following equation here. We get that rho is equal to P over Q, which is equal to P over 2 to the n times Q prime, which is equal to the sum of J in capital J of 1 over 2 to the n minus J times Q prime. And so this expression is an Egyptian expression. We can see here that it's 1 over some number and we're summing it. So it's a sum of unit fractions. Okay, so if Q prime is equal to 1, then P is less than 2 to the n, so that n is not in J, capital J, and that also is an Egyptian expression. So we got here that if Q prime is equal to 1, then it's an Egyptian expression, so it's a sum of unit fractions, and we're fine. So that happens when rho is in A. Now we're going to see what happens when rho is in B. So we describe a transformation T over rho and set it equal to rho hat, and we're going to say that let M be minimal for the property P over Q is greater than 1 over 2 to the m. So M is some integer that has that property. P over Q, for any P over Q, is greater than 1 over 2 to the power of n. So how do we know that such an M exists? Well, we can see that the following sequence, 1 over 2 to the t, converges to 0 because it's monotonic and bounded for t equal to 0, 1, 2, 3, all the way to infinity. So we can see that as the denominators get larger, the fraction's getting smaller. So then we can clearly see that P over Q will definitely be bigger than 1 over 2 to the m as m gets larger and larger, because the whole fraction gets smaller and smaller. Okay, so then now we can define the reduced fraction. We can define the reduced fraction P hat over Q hat by the following. So it's the transformation T times rho, and we're going to say that this is equal to rho hat, which is equal to P hat over Q hat, which is equal to P over Q minus 1 over 2 to the M. P hat over Q hat, which is equal to P over Q minus 1 over 2 to the M. And we can call this here just equation 5. Okay, so now we've already gone through all the definitions that we are going to use. We've already defined what it means for rho to be in B and for rho to be in A, and all of the fractions that are on the interval of 0 to 1 are going to be one of those. So now we have the theorem. The theorem is every rho in S has an Egyptian expression. So remember what this means. All this means is that every fraction that we can write in our modern mathematics between 0 and 1, every fraction can be expressed using Egyptian expression. So we can express them as sums of unit fractions. So let's go ahead and prove this now. So we're going to start off by letting rho equal to P over Q. And if rho is an A, then we have an Egyptian expression already given by equation 4, which I wrote over here. So equation 4 gives it to us in this form, and it's basically again a sum of 1 over some number, and we just have a sum of unit fractions. So if rho is in A, then we're done. It's already an Egyptian expression. So now let's suppose that rho is in B. Okay, so that means rho is equal to P over Q, which is equal to P naught over Q naught, with Q naught prime not equal to 1, because if it's equal to 1, then that's already an Egyptian expression, so we're going to focus on it being not equal to 1. So we're going to construct the following sequence: P naught over Q naught, comma P sub 1 over Q sub 1, comma dot dot dot, all the way to P sub R over Q sub R, where P sub R over Q sub R is an element of A, while the predecessors are an element of B. So that's how we're defining it. And then now we're going to let P sub S over Q sub S equal to P sub R minus 1 over Q sub R sub S minus 1.
7
Yeah, okay. Minus 1 over 2 to the M sub S minus 1. For S is equal to 1 to dot 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 R. Then M naught is less than M sub 1, which is less than M sub R minus 1, and P sub R over Q sub R is equal to P sub R over 2 to the N sub R times Q Q sub R prime, with P sub R less than 2 to the N sub R plus 1, and Q sub R prime is equal to Q naught prime, which is not equal to 1. Then using equation 9 and equation 4 that I've written up here, we can conclude that rho is equal to P over Q, which is equal to P naught over Q naught, which is equal to 1 over 2 to the M naught plus 1 over 2 to the M sub 1 plus dot 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 plus 1 over 2 to the M sub R minus 1 plus this sum over here, which is the sum of J in capital J sub R of 1 over 2 to the N sub R minus J times Q naught prime. And so this is going to be for some capital J sub R, which is a subset of the set 0, 1, 2, all the way to N sub R. And so this finally gives us the required Egyptian expression that we need if rho is in B. So we have shown that if rho is in A, then we get an Egyptian expression. And if rho is in B, then we also get an Egyptian expression that we've written over here. And we finally have the end of the proof.